right, so for question number 3, it asks us to talk about the mechanisms for the inotropic, lusotropic, and chronotropic actions for norepinephrine and acetylcholine on the heart. So when talking about this question, I'm going to go ahead and just kind of work through this flow chart here. It kind of explains exactly what's going on, and so we can kind of talk through it here. So if we have the stimulation of the beta-1 adrenergic receptor, that will lead us to an activated alpha subunit. And so if we follow this arrow over here to the right, we see that this is the interaction of an alpha subunit with an L-type calcium channel. And so we know that the inotropy or increased contraction is due to the levels of cytosolic calcium. And so if we have this interaction of the alpha subunit with this L-type channel, we will increase the open probability of calcium channels, which will increase the amount of calcium influx. If we increase calcium influx, we'll have an increase in calcium concentration. And if we have the increased calcium, it will induce the calcium release from the sarcoplasmic reticulum, which will then cause increased contractility, which is the inotropic effect, which is basically what inotropy is, which is increased contractility of the heart. So that is one pathway we can go down. If we come back up to the top here, after we have the activated alpha subunit, we will then see an increase in adenylyl cyclase, which will lead to an increase in CAMP, as we know, and also an increase in protein kinase A. And so this increase in protein kinase A can lead itself throughout 4 of these different pathways. So we'll start over here at the left and kind of talk through each one of them. So all the way over at the left, we have the phosphorylation of the L-type calcium channels. And that will cause the open probability of calcium channels to increase, which will be similar to what we saw over here on the right. Increased calcium influx, calcium concentration, and there will be more calcium released from the SR, causing increased contractility. So that's a similar interaction with what we saw from the activated subunit. Instead, protein kinase A will cause a phosphorylation of these L-type channels, but it will ultimately cause the same effect of inotropy. Next, we have the phosphorylation of the ryanodine receptor. Do you know the ryanodine receptor between the SR and the T tubules? Next, we will have the dissociation of calcitabin 2 from ryanodine receptor, which will lead to an open probability, increased open probability of the ryanodine receptor, which will cause an increase in calcium release by the SR, increased calcium concentration, and increased contractility yet again. This next section, we have the phosphorylation of phospholavin, which will lead to an increase of the Circa pumps, so that will reuptake the calcium more quickly. Increased calcium reuptake into SR, calcium stores. So we have an increase in calcium storage into the SR, which can lead its way over here to the left, the increased calcium release by the SR due to the increased calcium storage, and find its way down to the contractility. But we can also here have an increased speed of relaxation due to that reuptake of calcium. So that is what we call the lusotropic effect. If we have the relaxation that happens faster in opposition to the contraction happening faster, that is the lusotropic effect. And after that happens, we will have a decrease in the duration of contraction. If we have our speed of relaxation go up, then our duration of contraction will in turn go down. So finally, with our last pathway from protein kinase A, we have the phosphorylation of troponin 1, which will ultimately cause an increased off rate of calcium from troponin C, which will then lead to an increased speed of relaxation, which is the lusotropic effect, and a decreased duration of contraction. So depending on what the increase of protein kinase A does, whichever phosphorylation it undergoes, that will lead to an increased contractility of the inotropy or a decrease of the duration of contraction, which is the lusotropic effect. Okay, so continuing on for this question, we're going to talk about chronotropic actions in this mechanism. First, we're going to start with the flowchart for the positive chronotropic actions of the catecholamines. So to start off, we know we have the stimulation of the adrenergic beta 1 receptor, which will lead to an increase in adenylyl cyclase, as we know, which will cause an increase in CAMP, which are also our HCN channels. If we go over here to the right, this increase in CAMP will also cause an increase in pKa, which will lead to an increase in calcium influx. So this increase in calcium influx in chronotropic actions, as opposed to inotropic lusotropic, cause an increase in the steepness of the slope and an increase in heart rate, which we know it will cause an increase in the threshold will become more negative, and our heart rate will then also increase. So if we go back up to here to the increase in CAMP and HCN channels, we will have another pathway which will cause an increase in sodium influx. So that will also cause an increase in the steepness of the slope, or the decay of the membrane potential, which will then cause an increase in heart rate as well. So each one of these pathways is the positive chronotropic actions of these catecholamines and kind of the mechanism of how they work through the heart. So moving here over to negative actions of acetylcholine specifically, we'll start with the M2 receptors, muscarinic receptors, and starting over here at the left, we have the beta-gamma heterodimer, which leads to the increase of the opening of the GERK channels, which are the G protein activated inward rectifying potassium channels, which will lead to our membrane potential becoming more negative or hyperpolarizing and will cause a decrease in our heart rate. Second, here we have the stimulation of the alpha subunit from these M2 receptors, which will lead to a decrease in CAMP, which we know that the slope will flatten because of the decrease in the IF, which will also cause a decrease in our heart rate. The stimulation of the alpha subunit can also cause a decrease in CAMP, which will lead to a decrease in the I calcium, which will cause the threshold to become more positive, which will lead also to a negative heart rate, or a decreasing heart rate. So each one of these positive and negative chronotropic actions of these catecholamines can affect the heart and its contraction, relaxation under all of these different pathways.